And thank you all for coming and joining us for this blockchain meetup organized by Binary District. I'd like to take a moment to extend my gratitude to our partners, the Research Institute and Primalbase, both companies involved in the cryptocurrency space, albeit in different ways. The Research Institute has been contributing to the development of blockchain technology in a very important way for quite some time now, and Primalbase itself is contributing to the blockchain space by using the technology to build a decentralized tech hub and a co-working space. Binary District also organizes a number of events across Europe and other places. You can have a look at those meetups and events over here, just in case you're interested in attending them. But before I get started with this presentation, I want to take a minute or two to tell you a little bit more about myself, what I do, and how I got involved with blockchain and cryptocurrencies. And perhaps if you had asked me a year ago, I would have said that I'm simply a technology journalist. I cover technology for the Next Web. I've been going through a wide range of topics, anything ranging from security to social media to internet culture, to sex tech and all that jazz, whatever it comes. But recently I've been making a slow transition to cryptocurrency and blockchain, especially since halfway through last year, I guess. And at some point we decided also at TNW to open our own media sub-brand focused on cryptocurrency blockchain, which is now live, and it's called Hard Fork. I'm the main editor for that platform. And one of the reasons I like coming here at Binary District, this is actually my second time hosting one of these events, is because it's a very nice and cozy atmosphere. It's a good kind of mix of people who come from different backgrounds, some of them working in blockchain, others working in areas completely unrelated to blockchain, but all of them interested in learning more about cryptocurrency, blockchain, and everything that's happening in this space. And this is precisely why we're here tonight. We've come here to learn more about the latest developments in blockchain consensus mechanisms, and specifically with a focus on proof of stake tonight. But if we're going to have a fertile conversation about proof of stake, it is difficult not to go back to proof of work, which is the other consensus mechanism widely used at the moment. It's actually the one that's being used by most of the cryptocurrencies out there. I recently saw a research, I can't remember who conducted that, but I think it mentioned that the breakdown between proof of stake coins, or at least coins that use some sort of proof of stake, and proof of work coins is about 70 to 30% in advantage of proof of work. But that might be about to change very soon because we have lots of developments in that area. But before I get into proof of stake, so let me just give you a brief breakdown of what proof of work is and how it came to be. So, like anything else, it's an algorithm used to confirm transactions on the blockchain. It's currently employed by Bitcoin, Ethereum, some other very big, obviously a number of big cryptocurrencies as well, like Monero, Bitcoin Cash, if that's what you're into. Anyhow, but at the same time, so in proof of work, what we do is that we use physical resources. We use basically mining. We use hardware to mine, to confirm transactions on the blockchain by solving cryptographic puzzles. But as it turns out, solving these puzzles is not so easy. It's actually a pretty big technological challenge for a number of reasons. One of the reasons being that it's very, it's not all that efficient with energy. You might have heard about news that Bitcoin. That overall Bitcoin consumption is projected to be at around 71 terawatts hour this year only. If you're struggling to understand what that number means, let me just kind of give you some comparisons. Basically, it's the entire energy consumption used by the country of Chile in a year. It's enough to power more than 6.5 million US households, and it's just about at 50% of what the Netherlands uses in terms of electricity throughout the entire year. So, as you can guess, that's having a big impact on the environment. But other than that, proof of work consensus mechanisms also have other problems like scalability, and that has become ever more present in the media recently with recent news about Bitcoin network being congested, Ethereum network being congested. Now, With Bitcoin, we have the Lightning Network, which is helping the scalability problem a lot, especially recently. They've been making great strides in fixing, improving the scalability problem. But the energy problems still remain there. And proof of work has some pros, for all that energy that for all that energy that it consumes, it's very secure. That's one of the good things about it. But it is not very sustainable at this rate, which is why many people have started coming up in the blockchain space, have started coming up with new solutions. One of them is proof of stake. And unlike basically the fundamental difference between proof of work and proof of stake is that contrary to proof of work, which uses physical resources to confirm transactions on the blockchain and push the blockchain forward, essentially, proof of stake relies on virtual resources, and obviously using those has advantages, such as it's much more faster in terms of transaction throughput. It's also not as energy efficient, which allows you to scale faster and just have a more effective system which people can use all the time. But it comes with its own problems. There's always pros and cons that need to be explored in that system, and this is what we want to focus tonight. This is what we want to focus on tonight. But instead of me telling you about all of these little details, I'm gonna have someone else who is much more experienced than me come and tell you about that. But before that, I want to invite you all to share your thoughts and opinions on social media using the hashtags blockchain protocols and binary district, or just tweeting directly at binary district. I would also like to give another shout out to our partners, Primalbase and the Research Institute. And I want to encourage you all to be paying close attention to the talk during the talk. So because we're going to open the stage to the audience at the end, so you have your chance to ask questions about proof of stake, proof of work, consensus mechanisms, and anything else that you want to know. And now, without any further ado, our next speaker has more than 10 years of cryptographic research experience. He's been working in the cryptocurrency and blockchain space for the last couple of years. He's been a researcher in Denmark, in universities in Denmark. He's currently an assistant professor at the Tokyo Institute of Technology, and he's also one of the main driving forces behind Cardano's Ouroboros proof of stake mechanism. I know I totally screwed the pronunciation of that thing, but it's a very difficult word, and I think maybe our speaker can answer that. But please give a warm welcome to Bernardo David.
Well, thanks for the introduction. The pronunciation of Ouroboros is a mystery to us all. I guess not to the Greeks, but to me as well. So what I'd like to talk to you a little bit about is how we have sat through this development of proof of stake based consensus protocol for blockchains with provable security, meaning that we have mathematically defined the security of this kind of protocols and come up with a protocol that can be proven to achieve the security guarantees. It's actually a family of protocols, or only one. It's the Ouroboros protocol, Ouroboros Praos, and most recently, Ouroboros Genesis. And I'm going to tell you a little bit about the general structure of these protocols and the differences between themselves and how they achieve all these nice characteristics. So in this talk, I'm going to give you a brief introduction. It's a bit redundant, so go fast through that on the main POW issues and how POS can help solve that, and then go into the structure of all this family of protocols that I've just told you, and then conclude with a bit thoughts on the future of this kind of blockchain protocol. Well, basically, with proof of work, we have this clear distinction between the miners and the actual stakeholders. So if you have a token in a proof of work based scheme, you do not really control how the blockchain gets added to how the system evolves. The miners who have more computational power than you can actually decide which transactions go into each block, or if they want to attack your system, for example. And that's not so nice when you actually have investment in a blockchain-based system. You have the problem of diminishing rewards for mining. We know that every couple of years, the rewards get halved. So at some point, what will make the miners actually invest money into mining blocks for proof-of-work-based cryptocurrency? And finally, we know that the control of proof-of-work-based systems is highly centralized in the form of stake pools. Mining pools. I'm talking about proof-of-stake already. And that's not very interesting, as we want systems to be truly decentralized. We don't want a handful of people to have control over the whole blockchain. Now, given these issues, there are alternatives that have been proposed to solve this. Years ago even, some of them, such as proof of stake and proof of space. Now, proof of space, similarly to proof of work, requires you to dedicate a physical resource, in this case space instead of computing, to the functioning of the blockchain protocol. So you need to have a lot of space allocated to store data in order to generate a block, which is still depletion of a physical resource. And we chose to focus on the proof of stake idea because it allows you to achieve the same level of security as proof of work based schemes without requiring any physical resource that has to be wasted in a way. Now, let's think of the main differences between proof of work and proof of stake. First of all, on the side of proof of work, we can see that the more resources you have, the more control you have over the protocol. Not necessarily resources invested in that blockchain, but computational resources. If I have a large mining farm, I might be mining any proof-of-work-based blockchain that is based on the same hash algorithms as the hardware I possess. So I can quickly switch between chains if I want to attack one and move on to attacking the other or supporting another one, and that might be a problem. Also, the energy waste, it's obvious that proof of work requires a lot of energy to be wasted into the mining process, and it gets all that centralization from the mining pools. Now, on the other hand, for proof of stake, we have the fact that the more money you have invested in the system, the more tokens you control, the more control you actually have over the evolution of the blockchain. The people who hold more coins in a proof-of-stake-based blockchain, meaning they have a larger stake on that system, get to generate more blocks, get to choose which transactions get into the blocks, and finally have a higher degree of control over the system. It's energy efficient. These proof-of-stake-based schemes could be really run on a cell phone or even something much cheaper than a cell phone like this. You could run it on a Raspberry Pi, on any device with very constrained computational power. And in the end, you give the control back to the users of the blockchain system. You don't have miners controlling how your blockchain progresses anymore, but the people who are actually invested in that blockchain and using it on a daily basis, controlling how the blockchain is going to work. Now, let's think a little bit on the basic structure of any proof-of-stake-based scheme. What do you want from proof-of-stake-based scheme? Basically, what you want is that the people who have more tokens should get better probabilities of generating the next block. The people who have more tokens should be generating most of the blocks in that blockchain. And what we're going to do here is basically illustrate this with a lottery. So let's say we have these characters. As you know, I'm based in Japan, so I favor these Japanese characters from Ghibli Studio, and they have different amounts of coins. So Totoro to the left has 9 coins, Porco Rosso in the middle has 6 coins, and Chihiro to the right has 15 coins. And they will run a proof-of-stake-based protocol in order to construct their blockchain. So how does that work? Let's assume we have a magic lottery system that fell from the sky that will help us elect whoever generates the next block. We start from a basic Genesis block, as in every blockchain system, and in order to generate each of the next blocks, we are going to use our magic lottery. The lottery is going to select, in this specific case, one of the coins. And the person who owns the coins gets to generate the next block. So in this case, the lottery selected one of the coins owned by Chihiro, and Chihiro got to generate the next block. And for each block, we keep running the lottery. So it chose one of the coins owned by Totoro, and Totoro gets to generate the next one. And we keep running that, so on, so forth. Now, notice that this lottery will choose coins at random. So any of these coins has the same chance of being selected by the lottery mechanism. And the person who owns the coin has the right to generate the next block. So the more coins you own in the system, the more blocks you get to generate. Because each of these coins will be selected with equal probability, and the owner will have the chance to generate the next block. So here, with a system like that, assuming we have this magical lottery, we can achieve the goal of proof of stake. Now, given this very magical model where we assume a lottery exists, how do we even know that it's secure, and how do we even make that lottery happen without trusting a third party with a truly decentralized protocol? That's basically our contributions in the field of PoS. First of all, we introduced a formal model, a mathematical model for arguing about the security of this kind of system. We can show formally that if you have such a lottery, you will get a system that achieves the same security guarantees as Bitcoin, as the Nakamoto Consensus Protocol in Bitcoin. That's one side of our contributions. Now, on the other side, we have to construct a mechanism for that lottery. On our first paper on the original Ouroboros protocol, we have certain restrictions we have to assume in order to both prove that having the lottery is enough to achieve security and to construct the lottery itself. This protocol is currently being used by the Cardano project, which will also be adopting the next protocol that we came up with, which is called Ouroboros Praos, where we get better security, meaning security under more real-world assumptions, and also better efficiency. Now, what do we get for Ouroboros? In Ouroboros, we have to assume one thing that is a bit limiting. We have to assume that everybody running the protocol has synchronized clocks. So we assume that all the users have in their computers, in their cell phones, in all their devices, the same clock running with the same time. And using that, we can show that we can guarantee liveness and persistence, which are the main properties that you want from a distributed ledger, such as proof-of-work-based ledgers or proof-of-stake-based ledgers, given that the adversary controls only a minority of the stake, meaning that the adversary does not control more than 50%, or actually that the adversary controls less than 50% of all the tokens in the system. It's a similar assumption as in the case of Bitcoin, where you assume that the adversary does not control more than 50% of the hashing power, and if the adversary does, you have a 51% attack, and you can destroy the system. So in this case, instead of assuming that the adversary has limited computational power, we just assume that the adversary has a smaller investment in the system. If you think of it, the logics behind that is that if you invest a lot of money into a proof-of-stake-based system, enough money, let's say, that will allow you to attack the system, if you invest 51% of all the tokens of that system, would you burn your investment in order to attack the system? Well, you can. Same way you could buy a lot of mining equipment, make a really big mining rig, attack one system, kill that blockchain, but you still have not burned your investment. With a proof-of-work blockchain, once you have your big mining rig and you kill one blockchain, you can readily start mining the next one. So in this case, you would actually be burning your whole investment if you chose to attack the system where you invested a lot. That's one of the main driving forces behind considering this kind of system as well. Another limiting assumption that we have to make is that the adversary cannot hack your computers too fast. What do I mean? What I'm saying is that we have to assume that once the protocol execution starts, there's a bunch of people who have been hacked, who are going to be acting maliciously to break the blockchain for some reason. But after the execution starts, new people only become malicious, only start attacking the blockchain slowly, which is a limiting assumption that we're going to eliminate in Ouroboros Praos. Now, how do we do that lottery that I was talking about? The main idea is using this procedure called Follow-the-Satoshi. In Follow-the-Satoshi, you basically select one coin or one small unit of coin in the system, and the person who owns that coin is the one that's selected by the lottery. How can you do that? You can use a cryptographic hash function, such as SHA-2 or SHA-3 or any proper cryptographic hash function, to evaluate a random seed, giving you an output which we're going to treat as a number between 1 and the total number of coins in the system. So this output is guaranteed to be random because we have a cryptographic hash function. And if we have the seed chosen at random, then we know that for each new seed evaluated through this hash function, we're going to get a new random number, we're going to select a new random coin, and the person who owns that coin will be able to generate the next block. Now, the winner of the Follow-the-Satoshi is going to be what we call a slot leader, somebody who generates a block. But we still have the problem on how to generate this seed, which is the main problem in most proof-of-stake based protocols, how you generate the randomness used to select the people who are going to generate the blocks. And that's one of the things we answer in our work, apart from proving that if you have the lottery, you have a secure protocol. So we start by doing small advances on the protocol structure rather than trying to solve the whole thing at once. We start by partitioning time in the protocol in epochs. Each epoch is further divided into smaller time slots that we simply call slots. So here I'm representing the slots as E1 to EK. And in each of these slots, you can potentially generate a block. So as in Bitcoin, if you want to think of this as Bitcoin, each of the slots would be 10 minutes. Every 10 minutes, you can generate a block, basically. Now, what do? We will use our lottery mechanism, using that hash function to evaluate a random seed, to select a random coin, whose owner is going to get to generate the block, for each of these slots. So let's say we start from our Genesis block. Our Genesis block is going to contain a list of who owns each coins, the users who own each of the Satoshis or coins or ADAs in the system, and also a value guaranteed to be random that I call R in this slide. That value is going to work as the seed in the Follow-the-Satoshi procedure. So for each of these lots, what we're going to do is that we're going to evaluate that hash function on this random value. The random output is going to select a coin, and the owner of that coin gets to generate the block of that slot. Now let's look at this situation. What happened here? In the first slot, E1, nobody was online, so no block was generated. You move on to the next slot. In the second slot, the next slot, somebody was online and a block was generated, and that block will link up to the Genesis block. And we keep doing that. For each of these slots, we run the lottery, we run the Follow-the-Satoshi, we select the person who's going to generate the next block, and this person gets to generate the block if they are online. However, if they are not online, the block is not generated. That's the basic idea. So you also need people to be online. Now, you might be asking yourself, so if I own a coin, do I have to be online 24/7 in order to make sure that when my coin is selected by the lottery, the block is generated? That would be very annoying to require all the users to be online 24/7. That's why, as part of the system, we have a mechanism called stake delegation. you can delegate to a third party the right to generate the block on your behalf. You're not giving them your coin. They do not have control over your coin. They cannot spend it. The only thing they can do is prove that they were given the right to generate the block and generate this block even if you're offline. So you do not have to be online 24/7. Now, I say that we have an epoch, and we use the randomness that was given in the beginning of the epoch in order to run the lottery to select the person who generates the block in each slot. But this is problematic because this becomes predictable, right? I have this fixed list that shows which user owns each coin, and I have this fixed randomness. So what could happen here is that, let's say that in this block number 3, one of the users here who had a lot of coins, who had a lot of stake, transfers all of his coins to another person, and now he doesn't have any stake in the system. He's free to attack the system because he's not really going to lose any money. He already sold his tokens, and he's still shown here as the owner of the tokens. That's bad. But it's a caveat that you have to contend with in order to make the systems truly secure, in order to make the mathematical proofs go through. Now, how do we deal with that? We will make these epochs short in such a way that the amount of funds that get transferred here do not mean that somebody has completely lost all their stake in the system and can now freely attack it. But we also have to figure out a way to update this randomness for the next epoch. So we're going to run an epoch, find a way to generate some new randomness, and update this list according to the transactions that happened on this epoch. And we're going to make those epochs short enough such that the movement of tokens of stake in the epoch does not create this kind of situation where somebody completely got rid of all their tokens and is now trying to attack the system. The main problem here, well, of course, is proving that doing this is enough to get security, which we do in a series of very lengthy papers that I'll give you the link in the end of the presentation. But I'm not going to delve into the details of that proof because it would take me maybe several weeks talking about it to explain each of these small details. But what I would like to get you to understand is how we can actually use this structure and other techniques in order to make these epochs progress in such a way that we generate the new randomness and we update the list of stakeholders and coins they hold in a way that keeps our security guarantees meaningful, meaning that the people who currently own more stake really have higher probability of generating the next block. Now, in this protocol, we're going to run an epoch, and in parallel, we're going to run a procedure called coin tossing. A coin tossing protocol is a cryptographic protocol that allows a bunch of people who do not trust each other to communicate and in the end achieve a random value. They will output a random value that cannot be influenced by any of them and that is guaranteed to be perfectly random. And the G.O.D letters here mean that as long as we have 50% of the people acting honestly in the protocol, we are guaranteed to obtain this perfectly random value in the end of the coin tossing procedure. So we're going to use this technique in order to generate the random value R for the next epoch. Now, I run the first epoch, I run my coin tossing, I use the transactions stored in these blocks of the first epoch to update the list of stakeholders and the stake they hold, the coins they're holding for the next epoch, and I use the random value I have obtained from my guaranteed output delivery coin tossing protocol in order to update the randomness for the next epoch. So what have I achieved here? I basically have the first ever epoch of the protocol running using the stakeholder list that is in the Genesis block and this random value that is in the Genesis block. But after that, I can use randomness that was truly generated by the participants of the blockchain protocol, by the stakeholders, and I can update the list of stakeholders and the coins they hold in such a way that running the lottery in this next epoch will reflect the distribution of stake that resulted from the transactions conducted in the first epoch. So if somebody here sold a lot of their stake and somebody else bought more stake, they will have the proper probability of getting selected to generate a block in the next epoch. We need to do that for some reasons. I'm going to try to give an intuition to that. Let's say that we immediately updated this list after each transaction. Let's say that after each block, in order to select the person who's going to generate the next block, I just update this list of who has each coin according to the transaction of this block. This is a big problem. Why? Because I know that which coins are going to be selected in each of these lots, because I know this randomness, I know the cryptographic hash function, I can just evaluate this randomness and with the cryptographic hash function and find out which coin is going to be selected to generate each of these blocks. Now, if I'm a clever hacker, a clever adversary, what do? I evaluate all of this, and I start buying all these coins. And I start hacking into people's computers, people who own those coins. So I can, without controlling 50% of the stake, I can end up generating a majority of these blocks, and then I can implement a 51% style attack. So we cannot let the adversary know, he can know in this case, which coin is going to be elected to generate each block, but this distribution of coins and users is fixed. So the adversary cannot use this knowledge to rush forward, get all these coins, which are not most of the coins in the system, because here we have a small amount of slots, much smaller than the total amount of coins in the system. So the adversary could, with a small investment, buy all of these coins that are going to be used in succession. So we cannot let the adversary do that. That's why this list of stakeholders and tokens held by them gets fixed for the epoch. Until you generate a new randomness and a new list, and then of course the adversary cannot rush anymore because you have a new randomness that he could not predict that's going to tell us who is generating the blocks in the next epoch. And that's how the Ouroboros protocol goes. It constantly runs this lottery process with the current random value, and in parallel, it runs the guaranteed output delivery coin tossing protocol that will be used to refresh the randomness for the next epoch. And what we do basically is proving that this will give you a protocol that has the same security guarantees as a Bitcoin protocol. Though with the caveats that we assume that everyone is synchronized and that we assume that the adversary cannot simply hack all the people as soon as he wants, all the people who generate the blocks. Those are problems that we are going to solve in the Ouroboros PRAOS protocol. Now, a little bit of how this coin tossing protocol works. What we do is that we further subdivide the epoch in different stages. And in each of these stages, we use a protocol called commit then review coin tossing, which is an idea from the early 80s, from 81, from a paper that was actually called Coin Tossing Over the Telephone. And one of the examples people usually employ to explain this is saying somebody got divorced and they have a dog and they don't want to talk to each other in person to person, but they want to decide who gets the dog. They want to toss a coin, but they don't want to look at their faces, so they do it over the telephone. But then I could claim I got this or that result. But a coin tossing protocol allows you to get a fair coin toss, a fair random bit, without having to be physically present. we're going to use a bunch of cryptographic techniques to build such a protocol that both gives you unpredictable randomness, but also ensures that this randomness will be output, so that the adversary cannot try to break your coin tossing in such a way that in the next epoch no new randomness was produced. We also have the assurance that new randomness will be produced. That's the guaranteed output delivery I talked about. So we can build this from a number of well-understood cryptographic building blocks, such as verifiable secret sharing and commitments and so on. And we actually came up on a different thread than the Ouroboros protocols. We came up with a very interesting new protocol that can be used to generate these random values on blockchain. This protocol is called a scrape, and it uses this, it basically introduces a new way to do publicly verifiable secret sharing that is very efficient, and that you could run not only on Ouroboros or proof-of-stake based blockchains. You could run this protocol on any blockchain you want in order to get truly random values without trusting anyone, and with the guarantee that those values will be obtained. Now, I've claimed all that. What about proofs? Proofs are complicated. This is an expression from Japanese, mendokusai. It's too hard to explain these proofs. I don't want to keep you here for a month while I go through all the mathematical details of these proofs. But you don't have to believe in me that those proofs are correct. The papers describing these protocols, along with the mathematical analysis, have been published in the top cryptographic conferences like Crypto and Eurocrypt last year and this year. So this means that those proofs were peer-reviewed by a body of experts in cryptography who also believe that our work was done right. So it's not just me telling you that we have proofs and that they are correct. Other people have looked into that, very knowledgeable people have looked into that and deemed those things correct and interesting enough to be discussed in these top conferences. Now, as I told you before, we have a bunch of caveats in the first Ouroboros protocol, assuming the synchronicity, assuming that the adversary cannot immediately corrupt everyone during the protocol execution, which does not correspond to the real world, right? Because we do not have synchronized watches in the internet, tightly synchronized clocks. If you want to trust the NTP protocol for clock synchronization, you can, but I wouldn't trust that with a billion-dollar system. And we cannot assume this synchronization. That's simply not realistic. And we also cannot assume that the adversary will not hack whoever he wants to hack in succession in order to try and break the system. I wouldn't base a blockchain system security on the assumption that we have perfectly secure operating systems and implementations. We know we don't. These things get hacked. So what we do now in this next iteration of the protocol, Ouroboros Praos, is showing that even if you have an adversary that can hack people very fast throughout the protocol execution, and that nobody has synchronized clocks, we still get the same cool security guarantees. We get the same security guarantees as Bitcoin, without those caveats. Of course, it's still assuming that the adversary never controls 50% or more of all the tokens in the system. Similarly to the assumption that the adversary never controls 50% or more of the computational resources in a proof-of-work-based system. We do this by something we call a oblivious leader selection, which is the lottery. Instead of having this lottery where in the beginning of the epoch, I know everybody, every coin that will be selected for each slot, I'm going to do a lottery now that's kind of secret, that I will only learn that some coin and some person was selected to generate this block when they actually publish the block. Now, even if the adversary can immediately hack whoever he wants, even if you have a very powerful attacker who can choose, I'm going to hack these machines in the internet right now because I want to, even if you have that, it would serve the adversary no advantage because he doesn't know who is going to generate the next blocks anyway. So he wouldn't be hacking into the people generating the blocks. He would be hacking at random. And we do a lot of cryptographic heavy lifting to improve the efficiency of our randomness generation for the lottery. We still use that technique of hashing some randomness to generate a random number that selects a coin, but now we show that this randomness doesn't have to be perfect as before. We can have dirty randomness or biased randomness. And allowing this dirty randomness allows us to also generate it faster with much less interaction and much better scalability. So let's think a little bit of what we did here. First of all, we got rid of these synchronized clocks. Now we have this semi-synchronous model, which basically means that nobody has synchronized clocks. Nobody knows what time it is in somebody else's machine, but we know that messages will be delivered eventually. So let's say I am broadcasting a new block now. I know that at some point, maybe tomorrow, maybe in 1 month, everybody in the earth is going to see the block that I broadcast. But nobody knows what this delay is. The hacker, the adversary, can choose this delay in any way he wants. That's really what happens on the internet. I mean, if I broadcast a message now, I try to diffuse it now, who knows when it's going to reach China and Brazil and Antarctica? Nobody knows. I don't know the delays between all these connections. But now, with the Ouroboros Praos, we can handle this situation without sacrificing security. Also, as I said before, I said that the adversary who's trying to break your protocol can now just hack into anybody he wants at any point without any delay. And we still only need to know that the adversary does not control 50% or more of the tokens in the system. We have a very powerful adversary here, like a Machiavellic adversary. That's the picture in the slide. And how do we do that? We will use this building block called a verifiable random function, which is basically a function that takes an input and gives you a random output that cannot be predicted, but that allows you to publicly verify, to publicly prove that this output was really generated by this person who claims to have generated it. This primitive has a key generation mechanism similar to public key encryption or signatures that gives you a secret key and a public key. Now, once you have this key pair, you can send your public key to everyone. It's public. That will be used for verification. And you can use your secret key to evaluate this random function on a given input. You have an input X, you have your secret key, and that will let you evaluate the random function and obtain a random output that cannot be predicted and that looks random. It cannot be predicted even if you know the public key and the X, the input. It can only be predicted if you know the secret key. So only the person holding the secret key can know what the output will be. Now, we can verify this given the public key and the input and the output. We can say, okay, the output was correctly generated by whoever had the corresponding secret key to this public key from this input, or no, that was a fake output that somebody was trying to lie to you about. And this is the basic building block that will allow us to do the oblivious leader selection, to select the people who generate the next block without making it readily available to anyone in the protocol who is going to generate the next blocks in the slots. And it will also allow us to do the dirty randomness generation that is much more efficient than what we're doing before. Now, how do we do the private leader selection, this oblivious leader selection? We will evaluate the verifiable random function using each user's secret key on a random value. We still need this randomness. We'll use this random value and the number of the slot. So everybody locally, using their secret keys, evaluates the verifiable random function on this random information that we have agreed upon and the number of the slots. If the output is smaller than a certain function of their stake, they get to generate the block. So this function could be basically, if I have this much coins, if the output is smaller than the number of coins I have, I get to generate the block. If I have a lot of coins, my number of coins is higher, then the probability this output is smaller, is higher, and I generate more blocks. It's a bit more complicated than that in practice. We need a more fine-tuned distribution for this function, but the basic idea is that. And similar ideas were also proposed in Next, though not mathematically analyzed, and in Algorand, where they actually do have a mathematical proof that a similar idea will give you a good proof-of-stake-based system, though in a very different setting. The interesting thing is that we managed to construct and mathematically analyze this building block in such a way that we can guarantee that even if this protocol is run among a bunch of people in parallel, even if it's run inside HTTPS and other cryptographic protocols, it will remain secure. There's I think is a very big misconception that if you have a cryptographic protocol that is secure in isolation, meaning that you analyze its security assuming it's running by itself in a perfect world without other protocols, without other instances of the protocols. That's usually how you analyze some simpler models. If you have this analysis, it does not mean that your protocol is going to be secure in the internet. And in more cases than not, protocols that have been through this very simplistic analysis, or you just assume they are done in an isolated fashion, they break when you actually put them in the internet. So what we do that's new here is showing that we can construct with some new techniques a verifiable random function to do this oblivious leader selection with what we call universal composability security, which tells us that even if we put this running on the internet or in parallel with other protocols or with other copies of even the same protocol, we will still have the same security guarantees that we want to achieve. So we have this new analysis that shows we can actually construct these things with good security. We also need this other building block called key evolving signatures, which allow you to, once you sign a message, generate a next secret key that you will use to sign further messages and erase your current secret key in such a way that nobody can generate later in the future another signature for a previous key that was used in a previous point in time. And we'll use this to handle this case of adversaries that can immediately hack into people and steal their keys. The idea is, once you get selected to generate a block by that oblivious leader selection process, only you know that you were selected because you have your secret key for the verifiable random function, and then you're going to generate your block and sign it, saying, hey, I was the guy who was selected to generate the block. I'm signing it to say that, to show publicly that I'm that guy. But then what you will do is use the key evolving signature to erase the current secret key that used to sign this block in this point in time, generate the next secret key that can only be used to sign things in the future, and then you put your block out in the open. Now, even if you have a very smart adversary, a very smart agency that hacks into you and says, hey, now I hacked into you, I've blocked your message from the internet, I know that you were the guy who was elected to generate this block, I'm going to generate the block in the way I want and sign it. Well, they can't, because you have erased the key that could be used to sign that block. Now, you can only sign blocks in the future. That's the basic idea. Now, the third thing is that we come up with this dirty randomness generation, which is a simple idea to visualize but not really to prove. The idea is that what we do is that in every block, the person who generates the block, apart from signing the block, saying that they were selected by the oblivious leader selection process, they will evaluate their verifiable random functions on another piece of random data that we have generated. And in the end of the epoch, when you need to generate the random data for the next epoch, what you do is get these outputs of the verifiable random function that each block generator, each block leader put into their blocks, sum them all together, and hash them. And this will give us the randomness for the next epoch. The problem with this is that this randomness is not pure, this randomness is not uniform. The adversary, a hacker who's trying to break the system, can influence this randomness in certain ways. Then we go through a lot of pain to actually prove that this influence that the adversary has over the final randomness is limited, and given this limited influence, the lottery mechanism will keep working the right way that it should. But the good thing is that before we needed this coin tossing protocol where everybody had to communicate and put a lot of big stuff inside the blockchain. Now with this, all you have to do is put the output, a very short output, something like 256 bits of this verifiable random function inside the blocks you generate, and never talk to anybody else. Just see what's inside these blocks and check their validity using the public key of the verifiable random function scheme. Now, this gives you dirty randomness, but we show it's enough to achieve security, and it gives you much better efficiency. You save space on the blockchain, and it's easier to verify everything. There was still one caveat before that I didn't tell you about, but I'll tell you now before introducing Genesis, is that we still had to assume that when a new person joined the protocol, they would get from somebody they trust some intermediate states in the blockchain. Let's say every this many epochs, a block saying this was the first block of this epoch, and then first block of this many other epochs later, in order to bootstrap and reconstruct the chain. But this is not nice, right? We want to get something as in Bitcoin, where just from the Genesis block, you can verify the whole chain without having to trust anybody else. And that's what we managed to do in the Ouroboros Genesis protocol, which is the next iteration. We managed to now bootstrap the whole chain just from the Genesis block, just like Bitcoin. So now we have security without assuming that there's any synchronization in communication. We can let the adversaries hack you immediately, and we do not have these intermediate states we can bootstrap from the Genesis block. And we have the universal composability guarantee that even if this protocol is run in parallel with many other protocols, which it will be in practice, we will keep security. And that's the final point of this thread of research into proof-of-stake-based protocols. The way we get this now, the security without checkpoints, without these intermediate states, just bootstrapping from the Genesis block, is by using a more sophisticated chain selection rule. Instead of just selecting the longest chain, we select the longest chain that has a bunch of other properties. And that can be proven to give you security if you have only the Genesis block and nothing else. So that's basically that. Here are the links to the papers describing these protocols. They are not very easy to understand. Of course, it's a deep theoretical analysis on the protocol's operations and their security. But anybody who's interested in seeing the actual research that was done, you're very welcome to look at the papers. Don't be too scared by the weird mathematics in that. But it's good to see that they're publicly available. And both Ouroboros and Ouroboros Praos have already been published. I should update this slide. Actually, Ouroboros Praos appeared in Eurocrypt 2018, while Ouroboros appeared in Crypto 2017. Well, that was it. Thanks for your attention, and I'll be very happy to answer any questions now or offline or by email. Just please send any questions my way. I'll be happy to address them.
Thank you for sharing your insights with us, Bernardo. Right now, we're going to have a little fireside chat. I'd actually like you to stay with me.
Sure.
We're going to have the chat right now. Just 1 second to set up the chairs and everything else. In the meanwhile, think of your questions.
Chairs for you guys. Thanks.
So, sorry. As a journalist, I often ask the people that I speak with how they got into blockchain, and in this case, it seems like it was a natural transition as someone who does research in cryptography. But what I was interested about your specific case personally is how did you get in proof of stake? And was there ever a moment that you believe that proof of work is the solution that's gonna basically is gonna be the solution that's gonna work for blockchain, or at least some sort of a modified, version of proof of work? And what convinced you to move into researching proof of stake in the first place?
Well, I mean, proof of work is interesting. It does work. The only problem that we're seeing these days is that it creates a huge energy waste, and it seems to be not so scalable. So among all the alternatives that people had proposed, proof of stake seemed like a very interesting one, and more specifically one where I could apply my previous research experience in cryptography, since it needs all these tools for generating randomness and analyzing how this works. And that's the kind of stuff that I've been doing for a while. So it seemed like a natural direction to follow, as well as an approach that looks promising in achieving truly scalable blockchains.
So like we mentioned before, there's other companies in the blockchain space working on proof of stake solutions. And I was wondering, who do you consider your biggest competitors? And can you highlight one of the aspects that you kind of admire about their work? What makes their models interesting in your eyes?
There's two other proof of stake based protocols with full mathematical proofs that I think they're very interesting. And those are the Algorand protocol, though it works in a different model than the eventual consensus as blockchains. It works on a model where each block is 100% assured to be agreed upon by all the participants in the blockchain protocol at a cost of efficiency. You cannot generate blocks as fast as you do with any other given blockchain, but once the block is generated, you know there's consensus of that. You don't need to wait for the chain to grow on top of that block. But they do use a proof of stake based approach, and there's beautiful research involved in that, very interesting results. And on the other hand, there's a Thunderella and Snow White by the team in Cornell Tech, Rafael Passo and Lane Shi, that also achieves a proof of stake based protocol with provable security guarantees. They have put forth many interesting ideas that are certainly an inspiration for further advances in these protocols. And I believe each of those have interesting characteristics that they have introduced in the community and inspired more further research on top of that.
Can you perhaps envision Cardano working with one of these two companies on polishing proof of stake at some point, or at least creating solutions to kind of interact between the separate blockchains?
Well, as a researcher, I'm always happy to collaborate with any teams on new, interesting, open problems. So I would totally be open to working with more people on improving these protocols and so on.
I would like to open for questions from the audience. So if you have any questions, please raise your hand.
What is the main difference between this protocol and other proof-of-stake protocols that already exist, like NXT, for example? Well, what is the added value of it? Because we saw a lot of technical stuff, but I didn't get exactly how it differentiates between some protocols that work.
So the main added value is that all of this, for example, NXT, or Casper or so on, none of these protocols have any assurance that they actually work. There's no effort in proving that they are secure, that they do what they claim they do. In our case, what we did, and also these protocols, Snow White and Algorand, we take the approach of principled cryptographic research that has been developed back in the late 70s and early 80s, which is defining a mathematical model of security, constructing a protocol, and proving that this protocol does achieve this security. And with this, we achieve a level of security where we're not simply claiming this or that attack doesn't work. It's something stronger. It's not trying to eliminate attack by attack, but trying to show that the whole thing achieves some good, strong level of security. Apart from that, we also improve on several of the mechanisms used for generating randomness on-chain, for example, apart from proving that given some randomness, you get the security. And those mechanisms, they can be used for several other applications rather than proof-of-stake based blockchains. But the main contribution is to actually show how to do this right. How to, in many of these other protocols, they have different structures, and nobody can prove that those structures actually work. And I think that when you invest this amount of money on the system, it's very good to be assured that this will actually work rather than trust the word of one or two people.
So it's different structures. It's not one structure that is the proof of stake and then you prove that this works. It's actually different kind of proof of stake algorithms that are in Ouroboros and Casper or NXT, right?
So the general idea of proof of stake that all these protocols want to achieve is the same. Now, the security model we define captures this idea that given that the people with more tokens get to generate more blocks, we're going to get something secure. We capture that in that security model. Now, what we introduced that's new is a protocol, Ouroboros and Ouroboros and Genesis, that can be proven to actually get there. That can be mathematically proven to actually achieve this security, which is also the case of Algorand and Snow White.
And why do you think wouldn't Ethereum or Casper or the other protocols wouldn't work with Ouroboros? Like, is there any problem for Ethereum to work with Ouroboros?
Do you mean to achieve the same level of security?
Yeah, why don't they use this system if it's provenly the best proof of stake system?
Well, I'm not a business guy. I don't know why they don't want to, but, well, there's...
all the community is open source, right? So
yeah, I mean, these papers are publicly available. The implementation of Ouroboros that's running on Cardano is open source. Anybody can deploy that on any system they want. I believe that the Snow White and Algorand also have implementations that are available. Why people don't adopt that in these other schemes, I don't really know. I'm not really into the politics of this project, so I really focus on the research. But that's a good question, actually. We could ask them, why don't they adopt something that's known to be secure? Yeah, it's a good point.
Any other questions?
So usually I think what he's saying is that in many fields of study, people patent findings and the university gets a share of the patent, right? In cryptography, there isn't that much of a trend of doing that throughout. Maybe that will evolve, especially now with all these schemes being applied to products. But up to now, there hasn't been really a trend of patenting these theoretical findings. I know nothing about patent law myself, but I don't even know how you could get these mathematical models and protocols and turn that into a patent. I know some people do, but personally I'm not interested in patenting and restricting any of my work. I'm happy to get it out there and let people use it. I think that's personally how I like to do research. I want this knowledge to be freely available. I wouldn't want to charge people to use it, really. And then in the end, in terms of conflicts of interest, I haven't heard up to now of any university pushing people to patent these things or not. I don't think they're doing that. I'm, of course, happy to collaborate with the Cardano project in implementing these protocols and putting them out there. It's very nice to see the research being used, instead of just sitting on a research paper.
Any other questions?
When you say that the protocol is mathematical, probably to be safe, this sounds to me that I'm not a mathematician. I understand the concept, but I don't understand how there could be a system that is actually unhackable. So you are 100% sure that you made the system is totally unhackable, and you would.
That's a great question. The thing is, there are several layers on the implementation of the systems. I'm talking here, and what I work on is on the highest layer let's say, on the mathematical description of the protocol and understanding how it's secure. But of course, these mathematical models we work on are idealized. They assume that, well, if I wrote these instructions for the protocol, they must be followed exactly in order to achieve the security. And when you turn an algorithm into an implemented program, bugs happen, right? Even if you have an algorithm that's known to work, I mean, you can get quicksort and implement it wrongly and not get the results you want. And you can do that with any algorithm, any protocol. So going from this highly theoretical, high-level mathematical description to an actual running program is a very complex process that takes a lot of expertise. It's not simply getting what I wrote and coding. What the people in Cardano and IOHK that are developing this are doing involves several steps, basically first translating all this weird mathematical language into a formal description that the programmers can implement, then implementing this using languages such as Haskell that can be more easily formally checked for mistakes. And then the next level is once the compiler time checks go through, you have the actual program compiling and running, and the next step is checking against this formal verification that the final program corresponds what we intended for the protocol. So, and of course this process is still error prone. You can have, we're humans implementing things, we can make mistakes, so even if you go through all this trouble, you might still get to an implementation that doesn't completely do exactly what the mathematical paper described. So there's a very big distance between going from this purely theoretical research, that's what I do, and to the final product. There's lots of talented people in between that have to be involved in order to make sure. Personally, I wouldn't be able to implement anything like that. I'm a theoretical researcher, but there's lots of very talented programming language theory people looking into how you go from here, the mathematical description, to here, an actual running system that you can use on day-to-day. But it's a very good question. It's a complex process, and of course, when you look at this paper, you can't say that any implementation of it will be 100% secure. Implementing is a very complex thing.
Can I follow up?
Sure.
So let's say, for example, that there is an algorithm like SATU, something like this. We can say that it's not currently hackable because it hasn't been hacked. But it's not 100% provable that it's not going to ever be hacked because somebody can find a way to hack the system, something that nobody else thought of. Isn't it the same with Ouroboros? Like you prove now that, for example,
it's actually very different.
Okay.
So the design of hash functions is, there's actually ways to prove that you can make hash functions that won't be hacked and so on, but that doesn't yield practical systems. The design of practical hash functions involves coming up with structures and trying to attack them many times, and after you spend, let's say, 10 years attacking those hash functions and you cannot find collisions and break them, you consider it secure. That's how the hash function community works. They have these big competitions every this many years. They put forth their proposals and they spend many years trying to break them. But they don't have a proof that it's correct. Now, what we do, we prove that this is secure according to this notion of security, given, for example, that digital signatures exist. We need digital signatures to exist in order for Ouroboros to be secure. Now, if tomorrow somebody comes and breaks all of the digital signature schemes in the world, then you cannot make Ouroboros anymore, right? Because you needed this to be secure to begin with. Now, and you go that deeper and deeper. If you have a digital signature scheme, you can also prove that given that, for example, factoring large integers is hard, that you're going to have a secure digital signature scheme. And you're happy with that, it's a generic proof, you know, this can't be broken. But if tomorrow somebody comes up with a way to factor large integers, you can't really build digital signatures in that way anymore. So what we always do when we say that we prove something secure is that we prove that it's secure given that something exists. Yeah, now, if this you mean, I mean, a hard problem or a building block, if those turn out not to exist, then the security proof doesn't make sense anymore. But that's a good question, thanks.
I second that. Excellent questions. Do we have any more questions? Perhaps? Let's go.
What's next for you after Ouroboros Genesis?
Well, I'm not doing that much proof of stake research these days. What I'm working on is mostly on smart contracts with privacy preserving properties in such a way that you can evaluate smart contracts with private data, private inputs from a number of people, and just get the smart contract to evaluate, to have a proof that you evaluated, but without ever revealing this private inputs. An application of that, for example, is decentralized exchanges. They're truly decentralized. Nobody ever learns anything. They just get the result of the exchange, and so on. That's my main goal now. We're working on this series of techniques to make it possible.
Thank you all for the lovely questions. I actually have one more sort of as a follow-up to her question.
Yeah.
So I was taking a look at some research presented by Angelos Kiaias yesterday. I think it was from a year ago, but he showed a graphic where you can see that in the current implementation of Ouroboros, at the time that they were testing, it could handle up to, I think, something in the vicinity of 250 transactions per second. Well, now that's significantly more than Bitcoin's 7 to 10 and then Ethereum's 10 to 20. But at the same time, it's still much less than a structure or a system or a centralized system like Visa, MasterCard, of these. Has there been any improvements in that particular area? And can you imagine the technology kind of improving so you can also scale up the transaction throughput per second in the future?
With Ouroboros PRAOs, we can already achieve a higher transaction per second rate.
Can you share the number? Or
I don't really know the number. It's just looking, what we can say is that given that Ouroboros achieves this much, we can most probably achieve higher with Ouroboros PRAOs from the theoretical analysis. But it hasn't been implemented and benchmarked yet. So I wouldn't be able to say any concrete number. It's of course a big challenge to make the systems up to the scale of Visa or something like that, that does hundreds of thousands of transactions per second. But it's going slowly, right?
So what would happen if it turns out that you simply cannot improve on that particular metric? Because I assume that it's going to kind of obstruct growth. It's also going to perhaps become clear that blockchain, or specifically Cardano's blockchain, would not be ideal for certain use cases. How do you imagine that future in case if things don't work out the way that currently they've been going?
So we're actually already imagining that, and there's a much better solution than just improving the transaction per second throughput of one blockchain, either proof of work or proof of stake. It looks like the best way to go is to do blockchain sharding. So in a sharding system, what you do is that you have different people processing different transactions in parallel, in such a way that I can parallelize several instances of Ouroboros, for example, doing 250 transactions per second to get to 1,000 or 10,000, let's say, by running them in parallel in shards. So that looks like that's the way to go, instead of trying to tweak these protocols to get alone in one instance more transactions per second. I think it's probably going to be the best way to scale, but there's other proposals and solutions. Who knows?
Thank you so much for sharing your expertise with us tonight. With this, I think we're going to conclude the fireside chat. But I would still like to invite you to stay for drinks and some small snacks and also some networking. All of the drinks are provided by our sponsor, Primalbase. I would also like to remind you that Primalbase and Binary District are hosting a number of other events, including one in Berlin on August 9, which will focus partially on Ouroboros. I'm getting better. I'll get there at some point. I hope, often when I go to, even myself as a journalist, when I go to meetups like that and conferences, sometimes they answer some of the questions I've had and I leave with less questions. I kind of hope this is the case tonight as well. But there's also a magical thing about leaving with more questions, which kind of leaves you with the motivation to go and look into them, which leads to more and more questions. And then at some point you might even start liking what you do and reach a point where you can answer questions like that to audiences like you're today. And I want to thank you again for coming and being with us tonight. And I hope I see you at the next one. Yeah.